Okay, let's prove the theorem which says the greatest common divisor of the integers a and b, not both 0, is the least positive integer that is a linear combination of both integers. Okay, let's say the set T is a collection of linear combination of a and b. So it should be written by ma plus nb for any arbitrary integer m and n. Then right now we don't know whether a is positive or negative. So let's say 1a plus 0b, either 1a plus 0b or negative 1a plus 0b is non-negative. Okay, so one of them should be in this set, of course including 0, but it's not a big deal, so let's just accept that way. And that both of them are members of T, so that chosen one must be also in T. So which means T is not an integer. It's not an empty set. So it has at least one element in there. Then by the well-ordering property, there is a least positive integer in T. So that integer must be written by the linear combination of a and b for certain integer m and n. Let's say that integer is d. So d is ma plus nb, and at this moment m n is a kind of specific number, depends on the situation. Then by division algorithm, if we divide this integer a by d, then it can be written by a equals dq plus r for certain unique integer q and r, with this condition that r must be between 0 and d, including 0. Okay, then we have two conditions right now. The r, by arranging this equation, can be written by a minus dq, but d is a linear combination of a and b, so instead of d we can say ma plus nb. So a minus dq is a minus ma plus nb times q. Then after arrange it, we can say this should be equal to 1 minus mqa plus negative nqb. But clearly 1 minus mq, everything is just integers, so this must be also integer, and negative nq is also a integer. So this form looks like a linear combination of a and b once again. So the meaning is r must be also in T, the set T. But we know r must be in this, between 0 and d, and our assumption for d is the least positive integer in T. Therefore r should be 0. There is another thing. So if r is 0, then a is equal to d plus q, which means d must be a divisor of a. Okay, so you can finish the remaining parts of the proof.